Hello everyone, in this video I'm going to present my final year project about hand joint reconstruction from EEG signals with deep learning. The content is organized and structured in the following order. Brain-computer interfaces are systems that utilize neural activities to provide a non-muscular channel of communication with the external device. And there are two main BCI paradigms. Sensory motor rhythm BCI is a multi-class classification for discrete control. It may require months of learning, while motion trajectory prediction BCI predicts motion state from EEG signals. It provides smoother and natural control, which is suitable for complex tasks. The objective of this study is to develop EEG decoding models capable of reconstructing hand joints. The motivation can be summarized in 3 points. Firstly, hand and finger movements play a crucial role in executing various daily tasks. And secondly, the decoder can provide the device control with hands in a smoother manner. And lastly, the decoder can also benefit the hand motor function rehabilitation. Research has demonstrated that the EEG signals contain motion-related information like positions, velocities, and angular velocities. And studies have been conducted to reconstruct the upper and lower limbs, like the hand, arms, elbows, shoulders, and fingers. However, compared to hand and arms movement, fingers have received significantly less attention, especially in the non-invasive setting. A common thread in hand joint or finger joint reconstruction is that they tend to use linear models as decoders and genetic algorithms for EEG channel selection. Meanwhile, decoding EEG signals, which are inherently non-linear and non-stationary, is a complex task. Deep learning has emerged as a promising approach in the various BCI research fields, and the primary building blocks of deep learning for EEG decoding are convolution networks, recurrent neural networks, and self-attention mechanism. But there are problems about deep learning methods, like despite the variety of neural networks proposed for the decoding, most of them have been primarily tested and evaluated on classification problems, like emotion recognition and imagery classification. Moreover, as black box algorithms, the interpretability of these deep learning models remain a concern. This study addresses the research gap in finger decoding by experimenting with state-of-the-art deep learning neural networks to decode hand joint angles using new dataset of 20 healthy subjects in a non-invasive setting. And this study also applies explainable AI algorithms to interpret the parameters of neural networks, specifically the channel importance. And this study also demonstrates the feasibility of MTP-BCI based on hand joint movement, which can be insightful for the development of new types of BCI commands. Let's elaborate our methodology from data collection. The dataset for this study was gathered at Center for Brain Computing Research at Nanyang Technological University. 20 healthy subjects were involved in the study, and there are both execution sessions and imagination sessions. The motor task to perform was a grasp action, in other words, an open-close hand movement. The experiment environment is illustrated in Figure 1. The dataset is constructed by recording the EEG signals and kinematic data simultaneously. Data was collected from 64 EEG channels, and the placement of electrodes followed the 10-10 system. Table 1 summarizes the important information about the dataset, and Figure 2 provides 2 examples of kinematic information from the glove. We also find that not all joints have significant movement during the open-close actions, so the relevant joints are identified through the variances, such that only the joints with significant variance are selected for decoding. Figure 3 highlights the joints selected as the labels to decode, and they are circled in red. So in other words, there are 8 joints to decode. Algorithm 1 summarizes the main steps of data preprocessing, like epoching, refactoring, filtering, downsampling, and ICA for ocular artifact removal, then followed by the common average reference. The problem formulation is elaborated in Equation 1. Specifically, the model learns a mapping from EEG feature window to a multi-channel vector of joints. To construct a feature window, every sample point of the glove data at time t is extracted as a pivot point. Then the corresponding EEG period within t minus delta t to t is extracted as the feature window, where the delta t is the window length. Tenfold cross-validation is applied to evaluate the model performance, each fold with 6 motor execution trials. The decoding model is trained with 9 folds and evaluated on the remaining fold. The average R values of the 8 channels on the 10 test folds are reported. The evaluation metric we use is the Pearson correlation coefficient, in other words, the R value. And the labels are normalized bending angles, so the output of the models are clips within the range of between 0 to 1. The models experimented include the linear model, EEG-Net, deep convolution, shallow convolution, and ACRNN. In the following section, we will elaborate the results we got. Figure 4 demonstrates the average R value for each subject in the tenfold cross-validation setting using different models. Table 2 and Table 3 lists the performance and its standard deviation of different models. It can be observed that there is a significant difference on decoding performance among subjects. And the EEG-Net obtains the highest decoding performance over all the models. We also studied the impact of feature window size, which is an important hyperparameter. We find that the feature window, when it contains 2000 milliseconds information, the decoding performance reaches the optimum. Then we apply explainable AI algorithm to analyze the channel importance. We use the deep lift algorithm, and we divided them into 3 groups based on their decoding accuracy. The right figure demonstrates the channel importance on the scope. Figure A and B are 2 example reconstructed signals in orange lines, while the ground truth signals are visualized in the blue dashed line. In the future, we will focus on the enhancement of decoding accuracy and prediction robustness, particularly during the rest state and imaged state. Robust predictions can benefit the development of asynchronous BCI as well. Further exploration on the transferability of models from execution data to imagery data will also be conducted. In conclusion, this study addresses the research gap in non-invasive hand joint movement reconstruction by developing decoding models using state-of-the-art deep learning neural networks on a novel dataset. It is hoped that this study will provide valuable insights for follow-up research on MTP BCI, asynchronous BCI, and the development of new types of BCI commands based on hand joint movement.